My name is Zhizhe Yang from Hong Kong University of Science and Technology, and this is a joint work with Microsoft Research Asia and Wuhan University, China. Today I'm going to introduce our visible light positioning system to you, and this system has been demonstrated yesterday. Wearable devices, such as smart glasses and smart watches, are becoming more and more popular. We envision that accurate indoor positioning in wearable devices can enable numerous interesting applications, such as indoor navigation and even shelf-level recommendation. However, accurate indoor positioning is a very, very challenging problem, as you all know. And this problem becomes even harder for those tiny wearables that has limited resources. Recently, researchers proposed to leverage lighting bulbs to transmit location information through visible light communication. In this way, the receivers that is capable of decoding can be localized precisely through angle of arrival or distance measurement. In a high level, the localization method is quite similar to RF-based approaches, but for VLP, it can deliver more accurate results since the bulbs are densely deployed and the light beams are very directional. One of the basic problems in designing such an effective system based on visible light is how to avoid the flickering in the communication. Since human eyes can perceive the low frequency changes in visible light, it is very annoying to see the flickers. As you can see, right, it's very flickering. It's very annoying. In order to avoid flickering, VLC transmitters in current VLP system are working at an unnecessarily high baud rate for broadcasting location beacons. Although the high baud rate eliminates the flickering, it costs significant overhead for decoding. The client either relies on an additional light sensor that needs cumbersome calibration, or must process very high resolution image to extract roller shutting patterns. In addition to this overhead, the high baud rate of the transmitter also relies on the LED bulbs, and all of those overhead is difficult for wearables to afford. So here we ask our question: can we design a better VLP system that has less overhead, and can all of those overhead be eliminated? Our answer to this question is positive. Instead of changing the intensity, we propose to modulate information by changing the polarization of light. Since human eyes cannot perceive the changes in polarization, it is a flickering-free modulation. In this way, a much lower baud rate, which is enough to broadcast location ID, can be used in VLC transmitters. As a result, the decoding overhead in clients can be largely reduced. To realize this idea, we propose our VLP system called Pixel. To see how it works, here we began with the display mechanism of LCD. Each LCD panel consists of thousands of small pixels. The left part is the major component of each pixel. The leftmost one is a backlight. It keeps transmitting unpolarized light, which contains light with every polarization. In front of the light source, there are two polarizing films vertical to each other. For each film, its direction is shown in the line. Only the light with its polarization in the same direction can pass through the film. If the polarization of the incoming light is vertical to the film, then the light will be blocked. So after the first polarizing film, only the light with the vertical polarization is left. In other words, the backlight is polarized in the vertical direction by the first film. Between the two films, there is a liquid crystal layer. The magic is here. If the voltage of the liquid crystal is low, the structure of liquid crystal will twist the incoming light by 19 degrees. Now, note that the polarization of the current light is just parallel to the second polarizing film. The light will pass through this film and the pixel display bright at this time. On the other hand, when the voltage is high, the liquid crystal will not change the polarization of the passing light. In this case, the polarized backlight will be blocked by the second film since they are vertical to each other. At this time, this pixel displays black. This is the display mechanism of LCD. The design of our VLC transmitter is very similar to the mechanism of LCD. Here, we highlight two modifications. First, we use cameras on devices to receive the VLC signal. Second, we move the second polarizing film in front of the camera so that to ensure that modulation can only be received by the camera. Suppose that we enlarge this big pixel. We enlarge this pixel to be a super big pixel that can cover a portion of the lamp. That super big pixel is our VLC transmitter. The people in this case cannot sense the VLC transmission since there is no polarizing film in front of our eyes. Based on such VLC transmitters, our positioning system can be easily set up by attaching these tag-like transmitters in front of any light sources, including LED, fluorescent light, incandescent light, or even light source, or even solar light sources. With a tiny piece of polarizing film attaching to the camera, smartphones and wearables can receive the location of the VLC transmitter, and then they can use this information to perform very accurate positioning. Note that the VLC transmitter generates light with two fixed polarization according to the high and low voltage of the liquid crystal layer. But the polarizing film in the camera is not fixed due to mobility. Therefore, the real receiving situation is more complex and challenging than the fixed one. Without loss of generality, suppose the transmitter generates two polarizations as the figure shows. If the receiving direction is parallel to the low voltage case, the received signal is bright. Consider, on the other hand, if the voltage is high, the received signal is black. This is because the receiving direction is vertical to the passing light. Consider all the possible receiving directions. The received signal is shown in these blocks. Note that the difference between the up and the low block is a precondition for the communication. However, we observe in some directions there is no obvious difference between the two stages. Although we can ask the users to move their mobile phones or devices to better decoding directions, but this surely adds burdens for them. Can we do better? Our solution is motivated by the rainbow, in that white light consists of different colors of light. And we found that some material have the property called optical rotation dispersion. They can disperse the polarization of different colors of light into different degrees. A lot of material has such property, including solids such as quartz, which is a major component of glasses, and a liquid such as echo. With appropriate selection of the thickness of the material, we can make a filter to ensure that in any directions, the receiver can differentiate the stages of the transmitter according to the difference of the received color. In this way, the user's mobility has no significant impact on the decoding. After adding the disperser filter in front of the VLC transmitter, the camera of the client will get symbols in RGB space. When the transmitter is transmitting information by switching in different voltages, the received signal will jump between two different colors. To decode these three-dimension samples, we project them into the vector that connects the two color clusters. In this way, we can decode the one-dimension samples by thresholding. We implement our prototyping VLC transmitter with commodity components. All of them are very cheap. This is the big LCD pixel that is used for modulating the polarization. And this is a glass box which is filled with the optical rotation material that to serve as the disperser. We also developed apps for mobile phones and Google Glass to receive the VLC beacons and perform high accuracy positioning. Now we come to the evaluation. To evaluate the performance of the communication, we first put the receiver in different orientations. As we can see, without the disperser, the decoding SNR changed dramatically with the angles. Once we add the disperser, since we can decode from color difference, the SNR in different angles is much more stable. The VLC system also works well in different distance. Note that the successful transmission in up to 30 meters only requires several thousands of pixels from the camera. We highlight that our system also works well with even lower resolution, which means that it has potential for situations with extreme limitation on resources. The evaluation of the positioning performance to evaluate the positioning performance, we set up the transmitters in the setting of different indoor environment, and we perform VLP in different directions and locations. The maximum location error in three-dimension space is less than ½ meters. Here, we show the overall computational head of our client app. This is a CDF of the processing time of the decoding and the positioning. We can see that our smartphones can finish all the computation in less than 100 milliseconds. For wearables such as Google Glass with even lower CPU frequency, the processing can also be finished in about 200 milliseconds. To conclude, we first introduced a lightweight visible light communication method based on modulating polarization. Second, we propose to use a dispersion filter to handle the user mobility. And at last, we implement and evaluate our system with both smartphones and wearable devices. Result shows our solution is lightweight enough and can achieve very high positioning accuracy. Thank you.